Hello. Couldn't get Teams to log me in this morning. Something wrong with my Pearson email or something or another. So I'm going to do it this way instead. This is the paper that you were working on. We'd already done question 1, which was this one about the trolleys passing through the light gates. So we're starting with this one here, and the answers are on the screen, so you can pause it and check your answers, but I'll just point out these sort of important bits. So on this one, we've got magnet B floating above magnet A. We've got several dimensions on here, so we've got the diameter of the hole inside as well, and we've also got this cross-sectional view here, as though we've sliced through the magnet with the thickness. So on to the question. It's good on this question, unlike some other exams, because we're using a digital vernier caliper, which means that you've not got to actually read this sort of awkward scale here, although we will need to look at that again at some point. So in this first one, we're just asked, they're measuring the external diameter. What can we do to reduce systematic error? And also, what can we do to reduce random error? Okay, these two. Random error, by the way, is what some of you were calling human error the other day. Okay, AQA will not give any marks for human error. It needs to be random. Some specs do still allow the term human error, but AQA do not like it at all. So to reduce systematic error, this is essentially zeroing the equipment, making sure that when the jaws are closed, it actually reads 0. And there are two things we could do. I'm not so sure we needed, like Mr. Armstrong's done here, he's actually put how to correct that. I think checking there's no 0 error was probably enough, but in a longer question, how would you correct that? Well, some of them would have an actual reset button. This one does actually just says 0 just there. On others you would have to mechanically do it, but essentially you would close the jaws or set the equipment, whatever it was, to what should be 0, and then change the reading so that it was 0, because of course if it's not, every reading you make is going to be out by that amount. That's what we mean by systematic. And random error is almost always solved by taking multiple readings and calculating an average. We've got another reading now. You're told that they want to measure the inside, and you were asked to sketch the cross section of the magnet onto there to show how they would do that. That's what these two jaws here are for. That's why they've got flat surfaces on the outside. They often taking internal measurements. It might be inside a pipe or a hole, as we've got in the side of this magnet. So that's what your drawing should have looked like there. Like I say, if I'm going too quickly, just pause this, but obviously I'm trying to get through this so that you're not watching a half an hour video, so you can always pause it and see the answers. We've got another measurement taking place in this next part of the question, and bear in mind that we've got one measurement there, another one written on the screen there, another one written on the screen there, so we've got 3 measurements of the inside, the outside, and of the thickness, which we're going to use now, because now we're being asked to calculate the volume. What we want to do first is work out the volume of the whole magnet as though it was a solid object without that hole in the middle. So we're essentially doing pi r squared. To get r, we need to halve the diameter reading that we've got earlier in the question written on the screen of the calipers, that is. So we've halved that, that's now r, so we've got pi r squared. Okay, and that gives us the cross-sectional area, and then we multiply it by the thickness, which again we were given earlier on the screen when it was measured. So this is the same as the volume of any cylinder. It's the cross-sectional area multiplied by the length, or in this case thickness. Then we want to take away from that, of course, the missing the hole in the middle, because of course that is not the volume of the magnet, that's a gap. Same method though, because we measured that diameter of the hole earlier, so halve that to get the radius of the hole, and then we've got pi r squared. The thickness, of course, of the whole area is the same as the thickness we used before. So this is the answer we should be getting, so pause yours and see if you got something close to that. Should be pretty close. Now the student is putting bits of sort of blue tack onto magnet B here to change the height that it comes above A. Doesn't make it incredibly clear, it just says she adds modelling clay to reduce it by 50%. What they actually mean in this question, and it was in the examiner's notes afterwards, is she's gradually added this modelling clay to reduce it bit by bit to 50%. So that wasn't incredibly clear on this question. And from the results she got, she came to the conclusion that this was true, that the force that the magnet was putting on the other magnet, and remember this is equal and opposite, so the force that B is putting on A is going to be equal to the force that A is putting on B. She's concluded that that force is proportional to 1 over h cubed, and the k there of course makes that an equals rather than just a proportion, but still F is proportional to 1 over h cubed. Mr. Armstrong's just written a bit of blurb there about that misleading description. You have to describe an experiment to test that conclusion, and some of the things you could have said here, remember there are only 5 marks, we don't need to say all of these, that the same force that B puts on A is exerted on B by A, equal and opposite, Newton's third law, that you would vary the weight by gradually adding clay, and you would try and get several different masses, that to get the force, remember the mass must be multiplied by G, because a mass on its own is not a force. You would measure h using a ruler. You would probably do it more than once, maybe on both sides, because the magnet might not be sitting straight, to get an average height. In fact, unless it's a perfect magnet, it's very likely to not be sitting straight if it's levitating. And in terms of what you'd plot, and you should always try and get this in, because sometimes they will limit the amount of marks for the first bit, for the method bit up here that we did. You want to see the analysis bit as well. So we'd need to plot a graph here, ideally, of f against 1 over h, because we've said that f should be proportional to 1 over h. And so if that's true, your line will be a straight line that goes through the origin, and that will prove that what the student has predicted is true. You could also mention here that in that instance k would be the gradient. Now we're on to a question about radioactivity. The thing is with these papers, they quite often make out that you, well not make out, but they quite often lead you to think that you should know more about a topic than you do. We've not done much radioactivity this year. We've not done much about magnets this year, but it doesn't matter. They're just applying what you do know to unfamiliar situations. So here, this question is actually really about energy and momentum. And so we are asked to show that the velocity of an alpha particle is a certain value, this value here. We're given its kinetic energy, okay. We're given that twice for some reason, actually. And we're given the specific charge, and that's because what they want you to do here is know that the specific charge is charge over mass. Okay, and if we know it's equal to this number, and we know the charge of an alpha particle is going to be 2 lots of the charge on an electron, then we can work out the mass. Now some of you understandably will think, well, I can work out the mass anyway because it's 2 protons and 2 neutrons. So you could get it all from the data sheet without using this. For reasons that will become clear next year, the mass will be slightly different if you work it out that way, because in actual fact when you combine protons and neutrons to make a nucleus, they lose a little bit of mass, and that's actually how we get nuclear energy, by exploiting that fact. But for now you don't know that, so I think a great deal of people on this question would have worked it out using the numbers on the data sheet, and when rounded actually you would still get something that was approximately 2 times 10 to the 7, so it wouldn't matter too much. We're told that they travel in straight lines, and this is their range. We want to calculate the average force as it's stopped. Well, how on earth are we going to do that? The idea is we know how much kinetic energy they have to start with, and we are looking at the force required to reduce that, or to reduce their initial speed down to nothing. And we know that it does it in this time here. So what we're looking for really is the deceleration. to go from this speed down to 0 over this distance, what is the deceleration? And that's why we've used here a Suvat equation with those numbers in. Again, pause this if you need to. And that gives you quite a big deceleration, which it should be because it's moving very, very fast, but it's being stopped in a very short time, a very short space, even 3.5 centimetres. When we have the deceleration, what force is required to produce that deceleration? Well, it's this very familiar equation, F equals ma. So we've used our acceleration there, and the mass that we calculated earlier can't be penalised twice for this, so error carried forward if you got that mass wrong earlier. If you did get the right force, it would have been this force here. We are now told that it transfers its kinetic energy to air molecules and produces quite a lot of ions per centimetre over this range. Now the first thing we can do here is multiply those two numbers together, and that will tell us how many ions it's producing in this 3.5 centimetres. We want to know the average ionisation energy of a molecule of air. How much energy does it take to ionise a molecule? Well, first of all, let's take the amount of energy that the alpha particle has and divide by the charge on an electron to convert that into electron volts. So this is how much energy we've got to play with. And we know that it's creating this many ions. So if I divide it by that number, I will get the energy it's used to create each ion, which is the answer. Again, pause if you need to. This one again looks fairly complicated, but it's actually not too bad. This is a question with a fairly simple circuit around here, at least, power supply, resistor, but then we've got a gap here. So there is some metal here, there's a metal wire, but here we've just got this radioactive source. And what we're told is that when the radioactive source creates an ionisation event in here, that enables some of the charge to jump across the gap because it becomes a bit more conductive because of those ions that have been made. When that happens, of course, the circuit momentarily becomes complete. We're told that one of these events gives a current of this much across the gap for 1.2 nanoseconds, and we want to calculate the number of charge carriers that pass a point during this. So this is a very simple Q equals IT problem. The current is this number here that we're given. The time, of course, is this time here, making sure you get your milli and your nano right. 10 to the minus 9, 10 to the minus 3. And that will give us the amount of charge that's jumped across the gap or through any point in the circuit in that time. If I know that this is the number of the amount of charge that's passed, I divide it by the charge of one charge carrier, and this is the number of charge carriers in that amount of charge. So that will be your answer. Should be to probably less significant figures than Mr. Armstrong's used there, actually. Really we want this to 2 significant figures. I suspect you may have lost a mark by giving it that accurately. Then the radioactive source, having been positioned 10 centimetres above, is moved slowly towards the gauze, and that's what led to that event happening when it got close enough. Discuss how the PD across the gap varied as the radioactive source was moved. Let's just go back to the diagram. So let's rub some of this off so it's a little bit clearer what I'm talking about. There we go. If there's a gap over here, then the circuit is broken, and the potential difference that we are putting in at the battery over here must be the PD between these 2 points. That's the difference in energy. The battery is trying to put 4,500 coulombs, joules of charge by the. Let me start again. The battery is trying to put 4,500 joules per coulomb into the circuit, which is reaching one side of that break. And on the other side we have our coulombs of charge with no joules of energy, so the PD across the gap is the same as the PD across the battery. When the radioactive source moves closer and we allow some charge to flow, Some of our PD is now going to be used across this gap. We know that it all needs to be used in the circuit in a loop. So whatever is not used here is used across the resistor and vice versa. And so in this question we can say that in words. While no current flowed, the EMF across the gap is the same as the power supply. When it flows, okay, the PD across the gap will drop. But we can actually work out as well, because we know that this is the value of the resistor and this is the current that flows through the resistor. That is the PD that's lost across the resistor. So how much is lost across the gap? Well, the difference between the two, which is only 250 volts in this case. Then we have a refractive index question. Remember, the important thing here is you know what refractive index is. It is the ratio of the speed of light in a vacuum to the speed of light in the substance you're talking about. So we know here that in glass A, this number represents the speed of light, 3 times 10 to the 8, over the speed of light in glass A. And the first thing we're going to do to work out the refractive index of B is to work out the speed it travels at in A. So they've rearranged this already. Down here, speed of light in A, refractive index, and that's because we have both of these two things here. That gives us the speed in A. We are told that in B it travels 3.252% less quickly than it does in A. So here they've got this number and they've just taken that 3.252% off to get the speed in B. Now what we have is the speed in B, and of course we always know the speed in a vacuum. So using both we get the refractive index of B. Pause if you need to. Sometimes and again, this is something they're introducing in the paper. It's not something in your textbook or that you should already know, and it will be something different next year, as it always is. But sometimes we use the fact that refractive indices change when optical fibres are stretched to see how much something has stretched. And so we don't need to understand every bit of this question. All we need to know is that these little bands on here represent, these little sort of black bands, represent regions where the refractive index has increased and the distance between them is W. And it tells us that a maximum intensity of the light reflected down this optical fibre is produced with these regions that have had their refractive index increased. Don't worry if you don't understand that, because all we need to do really is look at this graph here, and this maximum wavelength, or this wavelength at the maximum intensity, is plotted on the y, and on the x-axis is the amount of strains. What we're saying here is the more stretched the cable becomes, the fibre becomes, the higher this wavelength of maximum intensity gets. And that's really all you need to understand about this, just the relationship between the two things. Because we're just asked that if a cable is used to raise and lower a lift to monitor the strain, the lift is at rest initially and then accelerates downwards. How does this wavelength change? Well, if a lift accelerates downwards, there is going to be less tension on the rope than if it were moving at a constant speed, or if it were certainly being accelerated upwards. That would be a great tension in the rope that holds the lift. So moving downwards, the strain on the rope is going to reduce, and that is one of the first things he has said here. What happens if the strain reduces? Well, look at this. If the strain goes down, so does this wavelength. That is effectively your answer. Okay, he has talked here to get full marks about what was happening initially when the lift is stationary. The tension is going to be the same as the weight, otherwise the lift would be moving up or down. Okay, if it's stationary, then the tension is balancing the weight of the lift. But then, as we said, the strain will decrease, which means that the wavelength decreases in the optical fibre measuring device. And he's added a little bit here, which is not necessary for the 3 marks, that at a constant velocity, the tension would equal the weight again, and so the wavelength would go back to the original value. Now we're asked which one of these is going to be better for measuring small changes in acceleration. Well, we want the one that has the biggest change of wavelength for a change in strain. What that means is a slight change in acceleration of the lift will produce a much more visible pattern on this device. So P is going to be better for that. And again, you could pause that, but that is the written explanation of that. And section C I didn't get you to do, so feel free to rewind, pause, check you understand what I've said, and if you don't, feel free to email me on that one and I'll happily explain it to you.